In the quiet expanse of the night sky, an illusion of serenity unfolds. Stars hang like frozen jewels, their light a timeless whisper from distant epochs, pinning the heavens in apparent stillness. Galaxies, those vast whirlpools of cosmic dust and fire, seem suspended in eternal repose, their arms outstretched in silent embrace. The vault above appears unchanging, a canvas where time itself has paused, allowing the mind to wander through infinities without disturbance. Yet, this tranquility is a veil, a gentle deception woven by the vast distances that separate us from the universe's true rhythm. Beneath this calm facade, forces churn in ceaseless motion, drawing the threads of existence into patterns far beyond the eye's grasp. At the core of our own galaxy, the Milky Way, a river of light spilling across the darkness, lies a hidden truth that shatters this illusion. Here in the densest congregation of stars, something immense and unseen exerts its dominion. It is a gravitational anchor, an invisible force that tethers billions of stellar wanderers in their orbital dance, preventing the galaxy from unraveling into chaos. This entity consumes without flame, pulls without touch, shaping the paths of worlds and suns alike. Observations from orbiting telescopes and ground-based arrays, capturing radio waves and infrared glows, reveal its influence. Stars whirl around, an empty point, their velocities defying ordinary explanations, as if ensnared by an unseen predator lurking in the shadows. At the center of our galaxy, where no human eye can see, a colossal presence waits. It does not shine, it does not burn, and yet it controls us all. This paradox defies intuition, a void possessing mass equivalent to millions of suns compressed into a singularity, a point where density becomes infinite. It warps the very fabric of reality, bending light's straight path into curves and loops, trapping photons in eternal orbits before they vanish into oblivion. Theories rooted in general relativity, tested through simulations and gravitational wave detections, describe it as a black hole, a region where gravity's grip is so absolute that nothing, not even light, can escape its event horizon. Born, perhaps, from the collapse of an early massive star, or the merging of smaller voids in the galaxy's turbulent infancy, it grows by accretion, drawing in gas, dust, and errant stars that venture too close. The heat of infalling matter generates flares detectable across electromagnetic spectra, brief outbursts that hint at the violence concealed within its calm exterior. What is Sagittarius A? How did it form? And how does this silent giant shape the destiny of the galaxy that is our home? As astronomers peer deeper with instruments attuned to the invisible, the mystery intensifies. Radio images pieced together from global networks of dishes show a ring of glowing plasma encircling the darkness, a silhouette against the cosmic backdrop that confirms its existence. Speculation arises from credible models. Perhaps it seeded the galaxy's formation, its gravity clustering matter in the universe's youth, fostering the birth of stars and planets. Or in a philosophical turn, it embodies the cycle of creation and destruction, where the end of one era fuels the beginning of another, merging with wandering black holes to evolve, influencing galactic evolution over billions of years. The closer we draw through data from space missions and theoretical explorations on preprint archives, the more it transcends mere astronomy. It becomes a sentinel at the edge of knowledge, challenging our grasp of space-time's curvature, where time dilates near its boundary and quantum effects might whisper of hidden dimensions. In this enigma, the universe reflects upon itself. Sagittarius A stands not as a destroyer, but as a guardian of balance, its presence ensuring the galaxy's spiral arms endure. Yet the suspense builds. What secrets lie beyond its horizon? in realms where physics unravels? Could it connect to other voids through unseen tunnels, bridging distant cosmos? Or does it hold the key to understanding the Big Bang's echoes, the initial singularities from which all arose? As we contemplate this colossal silence, emotion stirs, awe mingled with humility, for in its depths, the fabric of reality bends, inviting us to question not just the stars, but the very essence of existence. The night sky, once still, now pulses with unspoken wonders, drawing us ever inward toward the heart of the mystery. The night sky, a canvas of infinite depth, has long captivated those who gaze upon it. Its stars, like scattered embers, flicker with stories of creation, their light traveling across eons to whisper of distant worlds. For centuries, astronomers charted this celestial sea with telescopes that captured the visible mapping constellations and nebulae in a quest to understand the universe's architecture. Yet beneath this luminous surface, a hidden pulse thrummed, a rhythm not of light but of invisible waves, carrying secrets from the heart of the galaxy. In the early 20th century, this unseen language began to reveal itself not through the lenses of traditional observatories, but through the hum of radio static, a discovery that would unravel the cosmos's deepest enigma. In the 1930s, a young engineer named Carl Jansky stood at the edge of this revelation. Tasked with tracing the sources of interference disrupting transatlantic telephone calls, he erected a sprawling antenna in a New Jersey field, its wires stretched like a net to catch the whispers of the ether. Amid the crackle of earthly storms, Jansky detected a faint, persistent hiss, a signal that waxed and waned with the rhythm of the stars. Its origin was not terrestrial, but cosmic, emanating from the dense core of the Milky Way, where stars clustered in a blaze of light obscured by cosmic dust. This discovery, born from a mundane pursuit, was a quiet revolution. Jansky's radio waves, published in modest journals, hinted at a universe alive with energies beyond the visible, a realm where the galaxy's heart pulsed with unseen power. The echo of Jansky's finding stirred a new generation of explorers. Among them was Grote Reber, an amateur astronomer driven by a hunger for the invisible. In his Illinois backyard, he crafted a parabolic dish of wood and wire, the world's first dedicated radio telescope, a humble instrument that belied its transformative potential. Night after night, Reber swept the skies, mapping the faint radio emissions that Jansky had glimpsed. His charts revealed a celestial landscape where the Milky Way's center glowed with a mysterious intensity, its signals converging like tributaries toward an unseen source. These were not the gentle glows of stars, but the cries of something vast and enigmatic, as if the galaxy itself were broadcasting a message written in waves. Decades passed, and the tools of astronomy sharpened. By 1974, astronomers Bruce Ballack and Robert Brown turned their gaze to this radiant core, wielding the precision of advanced radio telescopes. Their observations, drawn from arrays that spanned vast distances, isolated a compact source of radio. Waves at the galaxy's heart, a point so small yet so potent, it seemed to anchor the surrounding chaos. They named it Sagittarius A, a title as understated as the mystery it unveiled. This was no star, no nebula, but something altogether stranger, a presence that emitted no light, yet exerted a gravitational pull that shaped the motions of everything nearby. The discovery was not a deliberate quest for a black hole. Astronomers had been chasing the source of peculiar radioactivity, seeking to unravel the galaxy's hidden mechanics. Instead, they stumbled upon a cosmic titan, its influence masked by the very stars it governed. The journey to understand Sagittarius A unfolded with the patience of a river carving stone. Over decades, telescopes grew more precise, their lenses and dishes attuned to the invisible. Infrared instruments pierced the galactic dust, revealing stars that danced in tight orbits around an unseen point. Radio arrays, linking observatories across the globe, captured the faint pulses of energy emanating from the core. Astronomers led by pioneers like Andrea Ghez and Reinhard Genzel tracked these stars with meticulous care, their motions revealing a truth that defied intuition. One star, a beacon in the crowded stellar waltz, traced a path so swift and curved, it could only be bound by a mass millions of times greater than the Sun, confined to a region smaller than our solar system. This was no ordinary object, but a gravitational colossus, invisible yet undeniable. The realization crystallized. Sagittarius A was a supermassive black hole, a void where gravity's grip was so absolute that light itself could not escape. Its event horizon, the boundary of no return, swallowed matter and radiation, leaving only traces of its presence in the form of radio waves and the frantic orbits of nearby stars. Theories rooted in Einstein's general relativity, tested through simulations and observations, described its nature: a singularity where space and time collapsed, surrounded by a maelstrom of heated gas and dust. The radio signals first detected by Jansky, refined by Rieber, and pinpointed by Balick and Brown, arose from this chaos as matter spiraled inward, radiating energy in its final moments before vanishing into the abyss. The discovery of Sagittarius A was not merely a triumph of observation, but a philosophical awakening. How had such a giant formed? Cosmological models suggested it might have emerged in the universe's youth, when massive stars collapsed into singularities, merging over billions of years to form a supermassive core. Alternatively, it could have grown by devouring gas clouds and smaller black holes, its appetite fueled by the galaxy's turbulent infancy. Data from NASA's orbiting observatories and global telescope networks revealed flares of energy, brief outbursts where infalling matter glowed before its plunge. These glimpses, paired with computational simulations, painted a picture of a cosmic predator, its gravity shaping the galaxy's structure, from its spiral arms to its star-forming clouds. Yet, the mystery deepened with each revelation. Sagittarius A was not just an object, but a question mark etched into the cosmos. Did its gravity anchor the Milky Way's formation, drawing matter into the spiral we call home? Could it hold clues to the universe's earliest moments, when singularities birthed galaxies? The stars orbiting its periphery, tracked with exquisite precision, moved as if in reverence, their paths a testament to its dominion. Yet their dance raised deeper questions. What lay beyond the event horizon, where physics unraveled? Recent theories published in scientific archives speculated that quantum effects at its edge might hint at hidden dimensions or connections to other realms, perhaps through wormholes threading the fabric of space-time. The discovery phase, spanning from Jansky's faint hiss to the mapping of stellar orbits, was a journey into the unknown. Each technological advance, from Reber's backyard dish to the global networks of the Event Horizon Telescope, brought clarity and wonder in equal measure. By 2022, a historic image emerged, a glowing ring of plasma encircling a dark shadow, the silhouette of Sagittarius A itself. This was no mere picture, but a monument to human curiosity, a bridge between the tangible and the unfathomable. The black hole stood as both anchor and enigma, its silence louder than the stars it governed. In its presence, the universe seemed to pause, inviting reflection. Sagittarius A, born from the hum of radio waves in a New Jersey field, had grown into a symbol of the unseen. Its discovery was not just a scientific milestone, but a meditation on the cosmos's duality. where light and darkness, creation and destruction intertwined. As astronomers continued their vigil, the Galactic Center revealed itself as a crucible of existence, a place where the invisible wrote the story of all that shines. The mystery of Sagittarius A, far from resolved, beckoned humanity deeper into the abyss, whispering of truths yet to be unveiled. The Milky Way, a spiral of light stretching across the heavens, has long been a beacon of wonder, its countless stars painting a portrait of cosmic serenity. For generations, astronomers traced its luminous arms, charting the paths of suns and nebulae with the precision of poets mapping dreams. The galaxy's heart, veiled by thick curtains of dust and gas, remained a distant enigma, its secrets locked away in a realm where light faltered. Yet, as the tools of science sharpened, a truth emerged from this obscured core, a truth so profound it shook the foundations of astronomy. At the center of our galaxy, an invisible titan reigned, its presence rewriting the story of the cosmos with a silent, unrelenting force. The revelation began with a paradox, a source of immense power, concentrated in a region no larger than the orbit of our planets, yet invisible to even the most powerful telescopes. Observations from radio and infrared instruments, honed over decades, revealed a gravitational anchor so dense it defied all known explanations. This was no star, no cluster of radiant giants, but a mass equivalent to millions of suns, compressed into a point where the laws of physics strained. The only entity capable of such a feat was a black hole, a supermassive one, its gravity so intense it warped the fabric of space-time, swallowing light and matter alike. This discovery, pieced together from the faint signals of spiraling gas and the frenetic dance of nearby stars, was a shock that reverberated through the scientific world, a testament to the universe's capacity to conceal its greatest wonders. The evidence was undeniable, etched in the motions of stars orbiting the galactic center. One star, a solitary beacon in the crowded stellar waltz, traced a path that captivated astronomers. Its orbit, observed with exquisite precision by teams using infrared telescopes atop remote peaks, was tight and swift, its velocity reaching fractions of light speed. This star, tracked over years, looped around an unseen point with a grace that belied its urgency, its path bending under the pull of a colossal invisible mass. Calculations, grounded in the principles of general relativity, confirmed the presence of a gravitational giant, its influence shaping the star's trajectory with a force that could only arise from a black hole. This was the first conclusive proof of a supermassive black hole at the heart of our own galaxy, a discovery that transformed speculation into certainty. The implications of this finding rippled far beyond the confines of the Milky Way. For centuries, galaxies had been seen as vast assemblies of stars, gas, and dust, bound by the gentle tug of mutual gravity. Now, a new paradigm emerged. At the core of nearly every galaxy, a supermassive black hole might reside, its unseen hand guiding the orbits of billions of stars, sculpting the spiral arms that define galactic form. Observations of distant galaxies, from the nearby Andromeda to the blazing quasars of the early universe, hinted at similar titans, their presence betrayed by jets of energy or the chaotic swirl of matter. Yet, to find such a colossus in our own galaxy, hidden beneath the glow of countless suns, was a revelation that shifted the lens through which the cosmos was viewed. The Milky Way, once thought to be a mere collection of light, was now understood as a system governed by an invisible sovereign. The shock of this discovery lay not only in its scale, but in its secrecy. For millennia, this supermassive black hole known as Sagittarius A had remained unnoticed, its influence masked by the galaxy's radiant veil. Only with the advent of modern instruments, radio telescopes spanning continents, infrared arrays piercing cosmic dust, did its presence become clear. The faint glow of gas and dust, heated to millions of degrees as it spiraled toward the event horizon, produced signals detectable across vast distances. These signals, captured by global networks of telescopes, revealed a ring of glowing plasma, encircling a dark void, the shadow of the black hole itself. This was no ordinary object, but a cosmic crucible where matter met its end, radiating energy in its final moments before vanishing into the abyss. The nature of Sagittarius A deepened the mystery. Its mass, equivalent to millions of suns, suggested a history of cosmic consumption, devouring gas clouds, stars, and perhaps smaller black holes in the galaxy's chaotic infancy. Theories, drawn from cosmological simulations and observations of distant galaxies, proposed that such giants formed in the universe's earliest epochs, when massive stars collapsed or primordial gas clouds coalesced into singularities. Yet, questions lingered. How had this colossus grown so vast, and what role did it play in shaping the Milky Way? Did its gravity anchor the galaxy's formation, drawing matter into the spiral structure we know today? Or was it a latecomer, forged through mergers in a turbulent cosmos, its appetite molding the galaxy's evolution over billions of years? The philosophical resonance of Sagittarius A was profound. It was not merely an object, but a paradox, a void that defined presence, a silence that commanded attention. Its event horizon, the boundary beyond which nothing escapes, marked a frontier where physics faltered. General relativity described its gravitational pull, but near its edge, quantum theories whispered of possibilities beyond current understanding. Could particles entangled at its boundary hint at hidden dimensions, as speculated in recent theoretical studies? Might its singularity, where space and time dissolve, connect to other realms through unseen pathways, as some models propose? The black hole became a mirror, reflecting humanity's yearning to grasp the infinite, its darkness a canvas for questions that stretched beyond science into the realm of wonder. The emotional weight of this discovery grew with each revelation. The most powerful force in the Milky Way had remained hidden, its influence unnoticed by generations who gazed at the stars above. Its silence was its strength, its invisibility, its dominion. Each observation, from the star's relativistic orbit to the glowing ring of plasma, peeled back layers of the cosmos's mystery, yet deepened its enigma. Sagittarius A stood as a sentinel, guarding truths about the universe's birth and evolution. It challenged the notion of permanence, suggesting that even galaxies, vast and enduring, were shaped by forces unseen, their fates tied to the whims of a dark sovereign. The scientific shock was not merely the identification of a black hole, but the realization that the galaxy's heart beat with a rhythm alien to human experience. It forced a reckoning with the unseen, a humbling acknowledgement that the cosmos's greatest powers might lie beyond the visible. As telescopes continued their vigil, capturing fleeting flares and tracing stellar paths, the mystery of Sagittarius grew, inviting humanity to peer deeper into the abyss. In its shadow, the universe revealed itself not as a place of light, but as a tapestry of forces, where the invisible wrote the story of all that shines. As the veil over the galactic center began to lift, astronomers turned to instruments that could pierce the impenetrable. The heart of the Milky Way, shrouded in vast clouds of interstellar dust, had long resisted the gaze of traditional telescopes, its secrets guarded by barriers that scattered and absorbed visible light. Yet in the realm of infrared wavelengths, a new path opened. These longer waves, emanating from the warmth of stars and gas, slipped through the cosmic haze like whispers through fog, revealing the crowded stellar nursery at the galaxy's core. Telescopes attuned to this invisible glow, orbiting high above Earth's distorting atmosphere or perched on arid mountaintops, captured images of stars that danced in unprecedented clarity. This technique, born from the need to unveil hidden worlds, transformed the obscured into the observable, allowing scientists to map the motions of celestial bodies that orbited an unseen sovereign. The pursuit deepened with the ingenuity of combining radio telescopes scattered across the planet's surface. By linking these distant dishes through precise timing, astronomers created a virtual instrument as vast as Earth itself, achieving resolutions that rivaled the sharpness of a needle's point. This method, relying on the interference patterns of radio waves collected from afar, unveiled the fine details of the galactic center's emissions. Waves from the core, stretching across light years, arrived at each telescope slightly out of phase, but when synchronized with atomic clocks, they formed a coherent picture. Such observations exposed the compact source at the heart, its radio signature a faint hum amid the galaxy's symphony, hinting at turbulent processes where matter teetered on the brink of oblivion. On the ground, observatories in remote havens harnessed adaptive optics to combat the blurring whims of the atmosphere. Atop the volcanic peaks of Hawaii, the twin telescopes of an island observatory employed lasers to project artificial stars into the sky, measuring the twinkling distortions caused by turbulent air. Mirrors, deformable and swift, adjusted in real time to counteract these ripples, sharpening images to reveal individual stars in the dense galactic throng. Similarly, in the high deserts of Chile, a quartet of telescopes used comparable systems, their beams converging to pierce the dust veil with infrared precision. These advancements, refined through decades of engineering, turned blurred smudges into pinpoint lights, enabling the tracking of stellar paths that curved under immense gravitational influence. Leading this charge were teams guided by Andrea Ghez and Reinhard Genzel, whose meticulous work spanned years of patient observation. Gez's group, utilizing the Hawaiian telescopes, captured infrared spectra and positions of stars near the core, plotting their orbits with the accuracy of a cartographer charting unknown seas. Genzel's efforts, centered on the Chilean array, complemented this endeavor, employing adaptive optics to solve the same stellar ensemble. Together, their data revealed stars whipping around an invisible point at velocities defying ordinary gravity. One star, in particular, completed its elliptical journey in a mere 16 years, its closest approach bringing it perilously near the unseen mass. These orbits, analyzed through Keplerian laws adapted to relativistic realms, converged on a single conclusion: a concentration of mass equivalent to millions of suns, confined to a space smaller than the solar system's breadth. This proof, irrefutable and elegant, confirmed the presence of a supermassive black hole, its gravitational embrace shaping the galaxy's innermost domain. As observations accumulated, fleeting phenomena emerged from the darkness. Sudden flares in X-rays and radio bursts that punctuated the otherwise steady hum. Space-based X-ray observatories, scanning the skies with detectors sensitive to high-energy photons, caught these outbursts, brief spikes lasting minutes to hours. These events, originating from the immediate vicinity of the event horizon, signaled hot gas accelerating to near-light speeds, its electrons spiraling in magnetic fields to emit synchrotron radiation. Ground-based radio networks corroborated these glimpses, detecting correlated brightening as matter plunged inward. Such flares offered snapshots of the chaotic dance, where blobs of plasma, heated to billions of degrees, orbited the black hole, before vanishing forever. Theories grounded in magneto-hydrodynamic simulations interpreted these as hotspots in the accretion flow, regions where magnetic reconnection unleashed energy in spectacular displays. Patterns began to crystallize from the data, painting a portrait of the black hole's environment. Accretion flows, these streams of gas drawn inexorably toward the horizon, revealed themselves as turbulent rivers of plasma, inefficient in radiating away their heat. Unlike the bright disks around more voracious black holes, this flow was geometrically thick, puffed up by thermal pressure, with matter accreting at a rate far below its potential. Jets, those collimated outflows of relativistic particles, appeared faint and intermittent, perhaps stifled by the black hole's spin or the surrounding mediums. Density, hot plasma, ensnared in looping magnetic fields, twisted and churned, driven by instabilities that amplified turbulence. Observations from millimeter-wave telescopes captured the polarized light from these fields, revealing ordered structures amid the chaos, filaments that channeled energy and matter, influencing the flow's dynamics. Yet as the picture sharpened, a deeper mystery unfolded. Why did this supermassive black hole remain so quiescent, its luminosity a mere whisper compared to the thunderous roars of other active galactic nuclei? In distant galaxies, similar giants, blazed with the light of trillions of suns, their accretion disks fueling quasars that outshone entire star systems. Here at the Milky Way's heart, the black hole accreted material at a fraction of the Eddington limit, the theoretical maximum where radiation pressure balances gravity, emitting energy equivalent to only a tiny portion of its capability. Data from infrared and X-ray surveys suggested a low gas supply, perhaps due to the galaxy's mature state, where star formation had depleted nearby reservoirs. Simulations, informed by hydrodynamic models, proposed feedback mechanisms. Past outbursts might have expelled gas, creating a self-regulating cycle that starved the black hole. Speculation, rooted in credible theories, extended to magnetic influences. Airborne observatories, soaring above atmospheric water vapor, detected far-infrared emissions that traced magnetic field lines threading the galactic center. These fields, amplified by the plasma's motion, could act as barriers, funneling gas into outflows rather than allowing it to spiral inward. In this interpretation, the black hole's environment resembled a cosmic sieve, where only sporadic clumps of matter breached the defenses, triggering the observed flares. Comparative studies with other galaxies, archived in astronomical databases, highlighted contrasts. Active nuclei often resided in merging systems where gravitational disruptions funneled abundant fuel. The Milky Way, relatively isolated, lacked such turmoil, leaving its central black hole in a state of dormancy. Emotional reflection stirred in the face of this quietude. The black hole, a potential devourer of worlds, chose restraint, its power, held in abeyance like a storm cloud that withholds its rain. This silence invited philosophical musing. Did it mirror the universe's balance, where destruction and creation danced in equilibrium? Or was it a temporary lull, a prelude to renewed activity should a star wander too close or a gas cloud descend? The flares, those brief illuminations, served as reminders of latent fury, glimpses into a realm where time dilated and space curved. As astronomers refined their models, incorporating general relativity's predictions with quantum insights, the black hole emerged not as a monster, but as a sentinel, its quiescence a testament to the cosmos's subtle harmonies. The investigation pressed onward, with each technique unveiling layers of complexity. Infrared views exposed the stellar cluster's demographics, revealing young, massive stars born in the black hole's shadow, their formation a puzzle defying tidal disruptions. Radio interferometry resolved the innermost accretion zone, its size comparable to the event horizon, where general relativistic effects warped light paths. Adaptive optics tracked orbital precessions, testing Einstein's theory in extreme gravity, deviations whispering of dark matter influences or alternative physics. Genzel and Gez's collaborations, honored with global recognition, exemplified humanity's collective endeavor. Their data sets a foundation for generations. Patterns in the flares suggested periodicity, perhaps tied to orbiting hotspots or magnetic cycles, models drawing from particle physics to simulate electron acceleration. Accretion flows, modeled as radiatively inefficient, explained the low luminosity. Heat trapped in the plasma led to expansion rather than radiation, a process observed in analogous systems across the universe. Jets, though subdued, hinted at energy. Extraction via the Blandford-Znajek mechanism, where black holes spin twisted magnetic fields into relativistic beams. Plasma dynamics, governed by magneto-rotational instability, drove turbulence simulations on supercomputers, replicating the observed variability. The mystery of quiescence deepened with multi-wavelength campaigns, coordinated observations linking X-ray satellites with ground-based radio arrays captured simultaneous flares, revealing spectral evolution from infrared to gamma rays. These events, rare and unpredictable, illuminated the transition from stable flow to chaotic infall theories, positing instabilities like Rossby waves or photon bubbles. Compared to Seyfert galaxies or blazars, where accretion rates approached unity, the Milky Way's black hole operated at a mere 10 billionth of capacity, its efficiency a conundrum. Speculative interpretations ventured into galactic evolution. Perhaps the black hole's growth peaked in the universe's youth, during mergers that built the bulge, now settled into quiescence as the galaxy aged. Data from gravitational wave detectors suggested past mergers, their ripples echoing through space-time, potentially aligning with the black hole's mass. Magnetic fields, mapped through Faraday rotation measures, showed a structured halo, possibly regulating inflow by launching winds that cleared their vicinity. In this deeper probe, the black hole transcended astronomy, becoming a philosophical touchstone. Its quietude evoked the impermanence of power, a reminder that even cosmic titans could slumber. The flares, like distant lightning, stirred awe, their energy a fraction of potential yet profound. As techniques evolved, future interferometers promising horizon-scale movies, the mystery promised further revelations, drawing humanity closer to the edge of understanding. The investigation, a tapestry of human ingenuity, wove together disparate threads: infrared's penetration, radio's resolution, optics clarity. Gez and Genzel's orbits, definitive in proof, anchored the narrative while flares and patterns unveiled dynamics. Yet, the quiescence lingered, a silent question mark, inviting reflection on the universe's rhythms. In the galactic heart, where matter met void, the cosmos pondered its own essence, its secrets flickering but never fully roaring. In the shadowed heart of the Milky Way, where stars swirl in a perpetual ballet of light and gravity, the enigma of the supermassive black hole deepens with each revelation. This colossal entity, possessing a mass equivalent to millions of suns, yet confined to a realm no larger than the solar system's expanse, embodies a profound contradiction. It harbors the potential to devour entire stars, its gravitational maw capable of tearing celestial bodies asunder in tidal fury, yet it feeds with a reluctance that borders on indifference. Observations from orbiting X-ray telescopes and ground-based radio arrays capture only sporadic infalls of gas and dust, trickling inward at rates far below what its immense pull might demand. This slow consumption, inferred from the faint luminosity of its surroundings, suggests a giant that slumbers, its appetite subdued by some unseen cosmic restraint. The universe, in its vast indifference, has placed this behemoth at the galaxy's core, where it could reshape worlds with a mere surge of activity, yet it lingers in quiescence, a silent sentinel amid the stellar throng. The flares that punctuate this calm offer glimpses of unrest, sudden bursts of energy that illuminate the black hole's turbulent domain. These events, detected across infrared and X-ray spectra by instruments scanning the galactic center, erupt without warning, brightening the region for hours before fading into obscurity. They arise from blobs of hot plasma orbiting perilously, close to the event horizon, where magnetic fields twist and snap, releasing pent-up energy in brilliant displays. Theories drawn from magneto-hydrodynamic simulations describe these as hotspots in the accretion flow, regions where gas compresses and heats to millions of degrees, emitting radiation as it spirals ever inward. Yet, their unpredictability evokes a sense of restlessness, as if the black hole stirs in its dormancy, testing the boundaries of its restraint. Each flare, meticulously recorded in astronomical archives, serves as a reminder of latent power, a flicker that hints at what might unfold should the influx of matter increase. When contrasted with the raging hearts of distant galaxies, the subdued nature of the Milky Way's central black hole becomes all the more striking. Quasars, those luminous beacons from the universe's youth, blaze with the intensity of trillions of suns, their supermassive black holes gorging on vast reservoirs of gas, unleashed by galactic mergers. Observations from space telescopes reveal these active nucleus cosmic furnaces, where accretion disks radiate across the electromagnetic spectrum, outshining their host galaxies and launching relativistic jets that pierce intergalactic space. In such systems, the black hole's hunger drives profound transformations, expelling gas in powerful winds that quench star formation or trigger new bursts of creation. Yet in our own galaxy, this drama plays out in muted tones. The Milky Way, a mature spiral with a relatively isolated history, lacks the violent collisions that fuel such spectacles, leaving its black hole to subsist on meager offerings from surrounding clouds and occasional stellar remnants. This contrast, illuminated by comparative studies of galactic evolution, underscores a fundamental puzzle. Why does this giant, with comparable mass to those in quasars, remain so restrained? Speculation arises from credible models, suggesting that the black hole may indeed be in a state of slumber, awaiting a cosmic catalyst to rouse it from repose. Cosmological simulations, informed by data from large-scale surveys, propose that its current quiescence stems from a depleted environment, where past feedback mechanisms, outbursts of energy from earlier accretion episodes, have cleared nearby gas, creating a zone of scarcity. Yet the galaxy is not static. Wandering stars or infalling molecular clouds could provide the necessary feast. Recent analyses of stellar orbits near the core reveal anomalies, perhaps echoes of a past merger, where another black hole collided with this one, altering its spin and surroundings. Such events, theorized in papers exploring binary black hole dynamics, could inject fresh material or realign magnetic fields, priming the system for renewed activity. Furthermore, measurements using advanced imaging techniques indicate a high spin rate, approaching 90% of its theoretical maximum, a property that could amplify energy extraction should accretion ramp up. In this speculative light, the black hole appears not dormant by choice, but poised, its rapid rotation a coiled spring awaiting release. The deeper investigation into its formation adds layers to this mystery. Evidence from polarized light images, captured by global telescope networks, suggests that the black hole may have originated from the union of two smaller progenitors, their merger billions of years ago, forging the giant we observe today. This process, simulated in computational models of galactic assembly, would have released tremendous gravitational waves rippling through space-time and potentially scattering nearby stars into eccentric paths. The presence of young binary star systems in its vicinity, discovered through infrared spectroscopy, challenges expectations as tidal forces should disrupt such fragile pairings. These findings hint at dynamic episodes in the galaxy's history, where inflows of gas from satellite mergers nourished star formation even in this hostile realm. Yet this narrative of growth contrasts sharply with the present calm, raising questions about the cycles of activity that govern supermassive black holes. Could periodic awakenings triggered by the galaxy's bar structure funneling gas inward explain intermittent flares? Or does the black hole's high spin, deduced from artificial intelligence analyses of vast datasets, indicate a mechanism for efficient energy dissipation without full activation? As the contradictions mount, the potential threat looms larger, a shadow cast across the galactic canvas. Should the black hole escalate to full activity, akin to the quasars of distant realms, it could profoundly alter the Milky Way's structure. Increased accretion would heat surrounding gas to incandescent temperatures, radiating energy that ionizes interstellar medium and disrupts molecular clouds essential for star birth. Powerful jets, propelled by the black hole's spin and magnetic fields, might erupt along its rotational axis, carving channels through the galaxy and injecting high-energy particles that accelerate cosmic rays. Such outflows, observed in other active galaxies, can extend for hundreds of thousands of light years, influencing the chemical enrichment of distant regions and potentially suppressing or enhancing star formation in vast swaths. In extreme scenarios, modeled in hydrodynamic simulations, this activity could reshape the galactic disk, driving outflows that expel gas and alter the spiral arm's morphology. The Milky Way, once a serene haven for life, might transform into a more volatile domain, its central regions bathed in radiation that challenges the resilience of orbiting worlds. This escalation, though speculative, draws from observed phenomena in analogous systems. In galaxies undergoing mergers, the influx of material awakens dormant black holes, leading to luminous phases that last millions of years. Our galaxy's future encounters, such as the anticipated collision with Andromeda billions of years hence, could provide such a trigger, funneling gas toward the core and igniting a quasar-like era. Even nearer-term events, a star straying too close disrupted in a tidal event, or a dense cloud like the one observed in recent passages, might spark temporary surges. These possibilities, grounded in orbital dynamics and gas flow models, evoke a sense of inevitability, a cosmic clock ticking toward change. Yet the black hole's current state, with its inefficient accretion and sporadic flares, suggests a delicate balance, where feedback loops maintain quiescence, preventing runaway growth. Emotional reflection stirs in the contemplation of this sleeping giant, whose gravitational shadow envelops the entire galaxy, including the fragile blue world that harbors life. Humanity exists in its thrall, orbiting at a safe remove yet bound by its inexorable pull, unaware of the rhythms that might one day shift. The flares, those restless stirrings, serve as omens, brief illuminations in the eternal night that whisper of potential awakening. In this vast arena, where creation and destruction entwine, the black hole embodies the universe's duality, a force of annihilation that also seeds renewal through the dispersal of enriched elements. Philosophical musing arises. Does its reluctance mirror a cosmic harmony where excess is tempered by restraint? Or is it a prelude to transformation, a quiet before the storm that reshapes destinies? The mystery deepens, drawing the mind into realms where science and wonder converge, inviting humanity to ponder its place in the gravitational embrace of an entity that slumbers, yet dreams of devouring stars. The contradictions persist, layered upon one another like strata in an ancient cosmic sediment. The black hole's mass, a testament to eons of accumulation, equips it with the capacity for voracious feeding, yet its environment conspires to starve. It, with gas densities too low to sustain a bright disk. Infrared surveys map these sparse inflows, revealing a puffed-up torus of plasma where radiation escapes inefficiently, contrasting with the thin, luminous disks of active nuclei. Magnetic fields traced through polarized emissions act as gatekeepers, channeling material into winds that evade the horizon. This inefficiency, quantified in efficiency parameters from theoretical models, underscores the reluctance, as if the black hole itself recoils from excess. Meanwhile, the unpredictable flares disrupt this narrative, their origins tied to instabilities in the flow, perhaps Rayleigh-Taylor fingers or magnetic reconnection events, that inject drama into the otherwise subdued scene. Comparisons to quasars amplify the intrigue, highlighting evolutionary pathways that our galaxy has thus far avoided. These are distant powerhouses, often hosted in elliptical galaxies born from mergers, accrete at rates approaching the physical limit, their bolometric luminosities rivaling entire stellar populations. Spectroscopic data reveal broad emission lines from ionized gas, Doppler broadened by orbital velocities near the black hole. In contrast, the Milky Way's core emits faintly, its spectrum dominated by thermal bremsstrahlen from hot gas rather than the non-thermal signatures of relativistic electrons. This disparity, explored in population studies of galactic nuclei, suggests that black hole activity correlates with host galaxy properties. Youthful disturbed systems foster activity, while mature spirals like ours favor dormancy. Yet, exceptions abound, with some quiescent black holes in merging pairs, hinting at nuanced triggers like gas-angular momentum or black hole spin alignment. The notion of slumber invites credible speculation on awakening mechanisms. Orbital resonances within the galactic barcode periodically drive gas inward, as modeled in N-body simulations, potentially leading to enhanced accretion over millennia. A close encounter with a stellar mass black hole, now confirmed roaming in, the Sagittarius region might culminate in a merger, injecting energy and altering spin. Such events, detectable through gravitational wave observatories, could precede a flare-up with the increased spin facilitating Blandford-Znajek extraction of rotational energy into jets. The young binary stars nearby, surviving against tidal odds, suggest recent gas infusions that might foreshadow larger inflows. In this framework, the black hole waits not passively, but in a state of potential, its high spin a harbinger of efficient future activity. The threat of escalation casts a long shadow over galactic stability. Full activation could launch bipolar jets, relativistic streams that heat the interstellar medium, altering temperature gradients essential for cloud collapse and star formation. Radiation feedback might ionize hydrogen across kiloparsecs, suppressing cooling and fragmenting molecular complexes. In extreme models, this could lead to a fountain-like circulation, with gas expelled from the disk only to rain back, enriching the halo with metals. The galaxy's structure, from its thin disk to its bulge, might warp under sustained outflows as seen in simulations of active galactic nucleus feedback. Life-bearing worlds, though distant, could face increased cosmic ray fluxes, challenging atmospheric integrity and biological evolution. In the emotional undercurrent of this narrative, a profound humility emerges. The sleeping giant, whose mass bends the paths of billions of stars, reminds us of impermanence, the cosmos as a stage where quiet interludes precede dramatic acts. Its restlessness, captured in flares, evokes a sense of anticipation, a philosophical meditation on awakening. We dwell in its shadow, our existence a fleeting note in the galaxy's symphony, uncertain of the stirrings that might reshape the heavens. The mystery ever deepening beckons toward understanding, where science illuminates the darkness, revealing not just facts but the poetry of existence itself. In the veiled sanctum of the galactic core, where the fabric of space-time weaves its most intricate patterns, the supermassive black hole known as Sagittarius A stands as a profound enigma. This colossal void, with its mass equivalent to millions of suns yet confined to a sphere no larger than the solar system's reach, defies simple comprehension. Astronomers, armed with data from global telescope networks and spaceborne observatories, have pieced together observations that reveal not just its presence, but the subtle mechanisms governing its behavior. Yet, as evidence accumulates, theories emerge like shadows lengthening at dusk, each one illuminating a facet while casting deeper mysteries. These ideas, drawn from rigorous simulations and spectral analyses, seek to explain why this giant feeds so sparingly, why its past echoes in vast structures across the galaxy, and how it might have grown from the cosmic dawn. In their essence, they probe the interplay of gravity, magnetism, and unseen matter, inviting speculation on the boundaries of reality itself. As the universe unfolds its secrets, Sagittarius A becomes a mirror reflecting the limits of knowledge, a silent oracle whispering of forces that shape galaxies and perhaps dimensions beyond. One prevailing notion posits that Sagittarius A suffers from a form of accretion starvation, a dearth of available gas that curtails its potential for voracious feeding. In the turbulent environment of the galactic center, where stars cluster densely and interstellar clouds swirl, one might expect a steady influx of material cascading toward the even horizon. However, observations from infrared and radio telescopes indicate that the accretion rate remains remarkably low, perhaps only a fraction of what gravitational theory would predict for such a massive entity. Data from NASA's Chandra X-ray Observatory and ground-based arrays suggest that surrounding gas clouds, heated to millions of degrees, expand outward rather than collapsing inward, driven by thermal pressures that counteract gravity's inexorable pull. This inefficiency arises from the galaxy's mature state, where star formation in the central regions has depleted dense molecular reservoirs over billions of years, leaving only diffuse plasma to trickle toward the black hole. Simulations informed by hydrodynamic models depict this flow as a geometrically thick torus, puffed up by internal energy, where radiation escapes poorly, further reducing the luminosity to mere whispers compared to the blazing quasars of distant realms. In this starved condition, Sagittarius A resembles a dormant predator, its hunger tempered by circumstance, subsisting on sporadic clumps of matter that ignite brief flares before vanishing into the void. Speculatively, this starvation might represent a self-regulating cycle. Past episodes of higher accretion could have unleashed winds that cleared the vicinity, creating a feedback loop that maintains quiescence until external perturbations, such as a passing star or infalling cloud, replenish the supply. Intertwined with this scarcity is the role of magnetic fields, those invisible architects that regulate the flow of plasma with tangled precision. Polarized light observations from millimeter-wave telescopes reveal ordered magnetic structures threading the galactic center, looping and twisting around Sagittarius A, like ethereal vines ensnaring an ancient tree. These fields, amplified by the shearing motions of orbiting gas, can become dynamically dominant, forming a magnetically arrested state where their pressure halts the inward spiral of matter. In such configurations, drawn from general relativistic magneto-hydrodynamic simulations, the magnetic flux accumulates near the event horizon, throttling accretion by launching outflows that carry away angular momentum and energy. For Sagittarius, with its inferred high spin rate approaching 90% of the theoretical maximum, these fields might extract rotational energy through mechanisms akin to the Blandford-Znajek process, channeling it into faint jets rather than allowing full infall. The result is a subdued environment where matter hovers in precarious balance, occasionally breaching the fields to trigger the observed X-ray and radio bursts. This magnetic regulation evokes a cosmic symphony where fields conduct the plasma's dance, preventing chaos from overwhelming the core. Credible extensions of this theory speculate that variations in field strength, perhaps influenced by the black hole's spin or external turbulence, could modulate activity over millennia, offering a pathway to understanding why some supermassive black holes rage while others, like our own, whisper. Echoes of historical violence further complicate the narrative, manifesting in the colossal gamma-ray bubbles that loom above and below the galactic plane. Discovered by NASA's Fermi Gamma Ray Space Telescope, these vast structures extend tens of thousands of light-years from the center, their symmetric lobes glowing with high-energy emissions that hint at cataclysmic events in the distant past. Theories posit that these bubbles are relics of Sagittarius A's earlier outbursts, when accretion rates surged, perhaps due to a merger with a satellite galaxy or the capture of a massive gas cloud. Simulations of such episodes depict relativistic jets erupting from the black hole, propelled by magnetic fields and spin, inflating the bubbles through shock waves that accelerate cosmic rays and heat interstellar gas. Spectral analyses reveal edges sharp with synchrotron radiation, suggesting inflation over millions of years, with the bubble's age estimated at around 10 million years, a mere blink in cosmic time. This past activity aligns with evidence of enhanced star formation bursts in the galaxy's history, potentially triggered by the same inflows that fed the black hole. In reflection, these bubbles stand as monumental scars, testifying to a time when Sagittarius A roared, reshaping the galactic landscape and dispersing enriched material that seeded new generations of stars. Speculatively, such eruptions might recur, driven by the galaxy's bar structure, funneling gas inward, reminding us that quiescence is transient, a pause in an eternal cycle of creation and destruction. The origins of Sagittarius A itself invite profound speculation on black hole growth models, questioning whether this giant was born massive in the universe's infancy or assembled through incremental mergers and collapses. Cosmological simulations, tracing the assembly of galaxies from the Big Bang's aftermath, suggest that supermassive black holes like ours may form from the direct collapse of primordial gas clouds in the early universe, bypassing the stellar phase, to achieve immense masses rapidly. Alternatively, hierarchical models propose growth via the coalescence of smaller black holes, remnants of massive stars in dense clusters, merging over eons as galaxies collide. For Sagittarius A, its moderate mass and the Milky Way's relatively quiet merger history favor a hybrid path: initial seeding from a stellar mass progenitor, followed by episodic accretion and minor mergers that built it to its current stature. Gravitational wave detections from facilities like LIGO hint at such processes, with ripples from distant mergers echoing the mechanisms that might have shaped a galactic core. The black hole's high spin, inferred from Event Horizon Telescope images and variability studies, supports a recent merger event, perhaps with an intermediate mass counterpart, aligning its rotation and injecting fresh material. This growth narrative reflects the universe's evolutionary tapestry, where black holes serve as gravitational anchors, their masses correlating with host galaxy properties in a co-evolutionary dance. Philosophically, it underscores the interconnectedness of scales, from quantum seeds to galactic spirals, each merger a union that forges new realities. Venturing deeper into speculation, connections to dark matter halos emerge as a tantalizing thread, linking Sagittarius A to the invisible scaffold that shapes the galaxy. Dark matter, that elusive substance comprising most of the universe's mass, forms vast halos enveloping galaxies, its gravitational influence guiding stellar motions and galactic formation. Around Sagittarius A, models incorporating dark matter profiles, such as pseudo-isothermal or fermionic distributions, predict subtle perturbations in stellar orbits and accretion dynamics. Observations of S-stars, those intrepid beacons circling the black hole, offer probes into this halo with deviations from Keplerian paths potentially signaling dark matter's density spike near the core. Credible theories extend this to self-interacting dark matter, where particles could form dense cusps or spirals in the halo, influencing the black hole's environment by altering gas inflows or stabilizing magnetic fields. In speculative realms, if dark matter consists of ultralight bosons, it might condense into solitonic structures around the black hole, mimicking additional mass and affecting event horizon scales. This interplay evokes a cosmic symbiosis, where the visible black hole and invisible halo entwine, their mutual gravity sculpting the Milky Way's form. Reflection stirs on the unseen's dominion, a reminder that the galaxy's architecture rests on foundations beyond light's reach. At the extreme edge, the event horizon itself beckons with speculations on exotic physics, challenging whether this boundary marks an absolute end or a gateway to quantum wonders. General relativity describes the horizon as a one-way membrane, where space-time curves infinitely, trapping all that crosses. Yet, quantum theories introduce paradoxes, such as information loss, prompting ideas like firewalls or holographic encodings where the horizon encodes the black hole's history. For Sagittarius A, Event Horizon Telescope, images reveal a photon ring encircling the shadow, testing these bounds, with deviations potentially signaling quantum corrections or alternative gravity models. Wormholes, hypothetical tunnels bridging distant space-time points, arise in extensions of Einstein's equations, perhaps stabilized by exotic matter, linking the horizon to other realms. Quantum structures, like fuzzballs in string theory, speculate that the horizon dissolves into a tangle of strings, preserving information without singularity. These ideas, while speculative, draw from credible frameworks tested against black hole shadows and gravitational waves, suggesting that Sagittarius might harbor portals or encoded universes. In philosophical contemplation, the horizon becomes a threshold, inviting humanity to peer into the abyss where classical and quantum realms collide, questioning the nature of reality itself. As theories interlace with speculations, Sagittarius A transcends its role as a mere astronomical object, embodying the universe's profound mysteries, its starved accretion and magnetic restraints, the echoes of past violence in gamma-ray bubbles, its growth through mergers, connections to dark matter, halos, and the enigmatic horizon all weave a narrative of balance and potential upheaval. In this cosmic drama, the black hole reflects the duality of existence, a destroyer that nurtures, a silence that speaks volumes. Humanity, dwelling in its gravitational shadow, grapples with these truths, humbled by the vastness, inspired by the unknown. Their galaxy's heart, once veiled, now whispers of origins and destinies, urging a deeper gaze into the eternal night. In the shadowed heart of the Milky Way, where the fabric of reality bends under the weight of an unseen colossus, the pursuit of truth has summoned humanity's most ingenious creations. The supermassive black hole at the galaxy's core, a silent, sovereign cloaked in darkness, yields its secrets only to those who wield instruments capable of peering through cosmic veils. Over decades, astronomers have crafted tools that transcend the limits of human perception, capturing whispers of radio waves, glimmers of infrared light, and bursts of high-energy radiation. These instruments, scattered across mountaintops and orbiting high above Earth's turbulent air, form a global orchestra, each note refining our understanding of the galactic enigma. Yet, as each layer of mystery is peeled away, new questions arise, drawing science to the edge of the abyss where gravity warps time and the universe tests its own laws. The tools of today and those poised on tomorrow's horizon weave a narrative of relentless curiosity, where the invisible is rendered visible and the silent speaks in echoes that resonate through eternity. The cornerstone of this endeavor is a global network of radio telescopes, synchronized to act as a single eye vast enough to span the Earth itself. This collaboration, uniting dishes from the icy peaks of Antarctica to the arid deserts of Chile, harnesses the interference of radio waves to achieve resolutions finer than any single instrument could muster. In 2019, this network captured a historic image, a glowing ring encircling a dark shadow, the silhouette of a supermassive black hole in a distant galaxy. Their triumph, born from years of synchronized observations and computational wizardry, revealed the event horizon's edge, where light bends into oblivion. 3 years later, in 2022, the same network turned its gaze inward, producing the first image of the Milky Way's own black hole, a faint, blurred ring surrounding a void, its shadow confirming a mass equivalent to millions of suns compressed into a region smaller than our solar system. This image, stitched together from petabytes of data, was no mere photograph but a testament to human ingenuity, a canvas where the invisible painted its own portrait. Thering's asymmetry, hinting at rapid plasma flows and magnetic turbulence, opened a window into the chaotic dance near the event horizon, where matter teeters on the brink of annihilation. Beyond radio waves, a fleet of observatories spans the electromagnetic spectrum, each contributing a unique thread to the tapestry of understanding. X-ray telescopes orbiting high above Earth's atmosphere capture the fleeting flares of high-energy photons emitted as gas spirals toward the black hole's maw. These instruments, with their detectors tuned to energies far beyond visible light, reveal bursts lasting mere hours, signaling clumps of plasma heated to millions of degrees as they orbit in magnetic fields. Their observations, cross-correlated with radio data, map the timing and spectra of these events, unveiling the dynamics of accretion flows where matter battles gravity's pull. Meanwhile, millimeter wave arrays in high-altitude deserts probe the polarized light from these flows, tracing magnetic field lines that twist like cosmic vines, regulating the influx of material and launching faint jets into the galactic void. Infrared telescopes, peering through the galaxy's dust-laden core, track the orbits of stars like celestial sentinels, their paths curving under the black hole's immense gravity, offering precise measurements of its mass and influence. The newest, sentinel in this armada, a space telescope with a golden mirror spanning vast distances, captures infrared light with unprecedented clarity, resolving the crowded stellar nursery at the galactic center. Its observations, begun in the early 2020s, reveal young stars and binary systems defying tidal disruption. Their presence a puzzle that hints at recent gas inflows or dynamical interactions. Together, these observatories weave a multi-layered portrait, each wavelength unveiling a facet of the black hole's environment. X-rays expose the violent infall, radio waves map the magnetic structure, and infrared traces the stellar dance. This symphony of light, collected across decades, transforms the galactic core from a hidden enigma into a laboratory where the universe's deepest laws are tested. The future promises even sharper tools, poised to unravel the mystery further. Why? The high plateaus of Chile, a colossal telescope under construction, dwarfs its predecessors, its mirror vast enough to gather light from the faintest stars. When completed, it will employ adaptive optics, using laser-guided systems to counteract atmospheric distortion, resolving stellar orbits with precision that rivals the finest needles threading cosmic cloth. These measurements will track subtle shifts in the paths of stars, testing whether their orbits align perfectly with Einstein's predictions or reveal deviations hinting at new physics, perhaps the influence of dark matter or alternative gravitational theories. Such precision could detect precessions caused by the black hole's spin, offering clues to its formation history and rotational energy, which may drive the faint jets observed in radio maps. Beyond Earth, a trio of spacecraft, planned for launch in the coming decade, will drift in formation across millions of kilometers, their lasers measuring minute ripples in space-time. This space-based observatory, designed to detect gravitational waves, will listen for the low-frequency hums of massive objects merging near the galactic center, perhaps a stellar mass black hole spiraling into the supermassive giant or binary systems, perturbed by its gravity. These waves, carrying signatures of the black hole's mass and spin, could reveal past mergers that built its immense size, offering a window into the galaxy's violent youth. Unlike ground-based detectors, which capture high-frequency bursts from smaller mergers, this mission will probe the slow waltzes of supermassive pairs, their echoes narrating the cosmic collisions that shape the Milky Way. Advancements in radio interferometry, building on the global network's success, promise to refine the black hole's silhouette further. Next-generation arrays, incorporating additional telescopes and higher frequencies, will capture time-resolved images, transforming static snapshots into dynamic movies of plasma flows near the event horizon. These sequences could reveal the orbits of hotspots, their periods testing predictions of general relativity in regions where gravity warps space-time to its limits. Variations in the photon ring's shape, influenced by the black hole's spin, and magnetic fields, may expose subtle effects like frame dragging, where rotating space-time drags matter along. Such observations, paired with computational models, will probe whether Einstein's equations hold in these extreme conditions, or if quantum corrections emerge, altering the horizon's structure. Ongoing experiments push the boundaries of general relativity, testing its predictions in the black hole's crushing gravity. The orbits of stars, mapped with infrared precision, exhibit relativistic effects, precessions and time dilations that align with Einstein's framework, yet their deviations are scrutinized for signs of new physics. Recent studies analyzing these orbits with statistical rigor Search for perturbations that might arise from dark matter spikes or hypothetical particles orbiting the black hole. X-ray flares, correlated with radio bursts, test models of accretion, dynamics, their timing and spectra, probing the interplay of magnetic reconnection and plasma turbulence. These tests, grounded in data from multiple wavelengths, seek to confirm whether the black hole's environment adheres to classical gravity or hints at quantum structures, such as fuzzballs or firewalls, that challenge the horizon's nature. Speculatively, these tools open doors to profound questions. Could gravitational waves reveal a merger history that links Sagittarius A to the galaxy's dark matter halo, its invisible mass-shaping orbital dynamics? Might the event horizon, probed by future interferometers, exhibit quantum fluctuations that encode information, resolving the paradox of information loss? Theories propose that the horizon could be a gateway, perhaps a wormhole stabilized by exotic matter connecting to distant regions or parallel universes. While such ideas stretch beyond current evidence, they draw from credible frameworks, tested against the black hole's shadow and stellar motions, inviting contemplation of realms where physics unravels. The emotional resonance of this pursuit lies in its relentless ambition. Each telescope, each spacecraft is a monument to humanity's desire to touch the untouchable, to map the unseen. The black hole, with its silent dominion, evokes awe and humility, a reminder that the galaxy's heart, though invisible, governs all that orbits it. The flares, captured in fleeting bursts, are like the black hole's breath, stirring wonder at its latent power. Philosophically, these tools bridge the tangible and the infinite, transforming data into poetry, where each observation is a stanza in the universe's epic. The ongoing testing, from stellar orbits to gravitational waves, probes not just a black hole but the essence of existence, where space, time and matter converge in a dance that defies comprehension. As these instruments evolve, the mystery of Sagittarius A deepens, each advance revealing layers of complexity. The global radio network, X-ray and infrared observatories, and future giants like the Colossal Chilean telescope and space-based wave detectors form a continuum of discovery, each building on the last. They test the limits of gravity, seeking cracks in Einstein's edifice or confirmations of its elegance. In this cosmic arena, the black hole stands as both anchor and enigma, its shadow a canvas for humanity's quest. The tools, ever sharper, draw us closer to the abyss, where the universe whispers its secrets, inviting reflection on our place in their reality, shaped by forces unseen, eternal and sublime. In the grand tapestry of the cosmos, where stars weave their luminous threads across the infinite night, the heart of the Milky Way beats with a silent rhythm. At its core lies a presence both invisible and omnipotent, a supermassive black hole that anchors the galaxy's spiral dance. This entity, a void of unimaginable density, commands the orbits of billions of stars, its gravitational embrace shaping the destiny of worlds scattered across light years. Every star that glimmers in the night sky, every planet that cradles the possibility of life, every atom forged in stellar furnaces, all move under the command of a darkness that eludes the eye. This colossus, known to astronomers as Sagittarius A, is not merely an object of study but a profound enigma, a silent architect whose influence weaves order from chaos, binding the galaxy into a singular, enduring form. As humanity peers into its depths, the black hole becomes more than a cosmic phenomenon. It emerges as a mirror reflecting the universe's deepest truths, a paradox where destruction and creation entwine, and a mystery that beckons toward the edges of existence itself. The duality of Sagittarius A casts a shadow both fearsome and sublime. It is a force of annihilation, its event horizon a boundary where matter and light surrender to oblivion. Yet it is also a cornerstone of cosmic order, its gravity orchestrating the Milky Way's spiral arms with unyielding precision. Observations from global telescope networks reveal a mass equivalent to millions of suns, compressed into a region smaller than our solar system, a density so extreme it warps space-time into a labyrinth from which nothing escapes. Without this gravitational anchor, the galaxy might never have coalesced as it did, its stars scattering into the void rather than gathering into the radiant spiral that cradles our world. Cosmological simulations suggest that supermassive black holes, like the one at our galaxy's core, may have seeded galactic formation in the universe's youth, their gravity drawing gas and dust into dense clusters that birthed stars and planets. In this light, Sagittarius A is not merely a destroyer but a creator, its silent power forging the conditions for the galaxy's existence, a paradox where the absence of light fosters the brilliance of countless suns. This duality extends to its very nature, silent yet commanding, invisible yet omnipresent. Unlike the blazing quasars of distant galaxies, whose supermassive black holes radiate with the fury of trillions of suns, Sagittarius A remains subdued, its accretion rate a mere whisper of its potential. Infrared and X-ray observations capture fleeting flares, brief outbursts where clumps of plasma ignite, before plunging into the event horizon, yet these are but flickers compared to the cosmic infernos elsewhere. This restraint, possibly due to a starved environment or magnetic fields that throttle inflow, evokes a sense of restraint, as if the black hole chooses to hold its power in abeyance. Yet its silence is deceptive. The gamma-ray bubbles looming above and below the galactic plane, discovered by space telescopes, testify to past eruptions when Sagittarius A roared, reshaping the interstellar medium and scattering enriched elements across vast distances. In this interplay of quietude and violence, the black hole embodies the universe's eternal balance, where moments of destruction give rise to epochs of creation. The emotional resonance of this cosmic giant stirs profound reflection. Humanity, dwelling on a fragile world orbiting a modest star, exists within the gravitational shadow of this unseen colossus. The stability of the Milky Way, its spiral arms cradling countless systems, owes its form to the black hole's enduring presence. The atoms in our bodies, forged in stellar cores and dispersed by supernovae, may trace their journeys through the galaxy's heart, influenced by the tidal forces of this invisible sovereign. Data from stellar orbit studies, tracking stars that whip around the galactic center at relativistic speeds, confirm its mass and influence, anchoring the galaxy's structure over billions of years. Without Sagittarius A, the delicate equilibrium that allowed life to emerge on Earth might never have existed, its gravity a silent guardian of the cosmic order that sustains us. This realization evokes a humbling awe, a recognition that our existence is tethered to a force both alien and essential, a darkness that nurtures light. Beyond its role as a galactic anchor, Sagittarius A challenges the very foundations of physics, pushing the boundaries of space, time, information, and causality. General relativity, Einstein's elegant framework, describes its gravitational grip with precision, predicting the orbits of stars and the bending of light near its event horizon. Yet, at the horizon's edge, Where space-time curves infinitely, quantum mechanics whispers of paradoxes, information loss, where the histories of particles vanish, or holographic encodings, where the black hole's surface holds the secrets of its interior. The photon ring, captured in historic images by global radio telescope networks, tests these theories, its shape probing whether Einstein's equations hold or if new physics emerges in extreme gravity. Speculative models, grounded in string theory or loop quantum gravity, propose that the horizon might dissolve into a quantum fuzz, preserving information in structures beyond classical understanding. Others entertain the possibility of wormholes, tunnels stabilized by exotic matter, linking the black hole to distant realms or parallel realities. These ideas, while stretching beyond current evidence, draw from credible frameworks, inviting contemplation of a universe where the boundaries of reality blur. The broader reflection turns to the black hole's place in the cosmic order. Is Sagittarius, how unique, a singular giant sculpted by the Milky Way's quiet history, or one of countless quiescent titans shaping galaxies across the universe? Observations of other spirals, from Andromeda to distant systems, reveal supermassive black holes. At their cores, their masses correlating with galactic properties in a co-evolutionary dance. Yet, the subdued nature of our black hole compared to the raging nuclei of quasar-hosting galaxies suggests a spectrum of behaviors influenced by environment, spin, and merger history. Does the black hole create the galaxy, its gravity seeding, the collapse of primordial gas, or do galaxies forge their black holes, nurturing them through mergers and accretion? Simulations of galactic formation favor a symbiotic relationship, where black holes grow alongside their hosts, their feedback, shaping star formation and gas dynamics. This interplay raises a profound question. At the heart of the void, does an ultimate truth about reality wait to be revealed, encoded in the physics of singularities or the quantum whispers at the horizon's edge? The mystery of Sagittarius. A transcends astronomy, becoming a philosophical beacon. Its silence speaks of restraint, its power of creation, its darkness of the light that defines our home. The gamma-ray bubbles, relics of ancient outbursts, remind us of its potential to reshape the galaxy, while its current quiescence offers stability, a cosmic cradle for life. The stars orbiting its periphery, tracked with infrared precision, dance in reverence, their path is a testament to its dominion. Yet the horizon beckons with unanswered questions, where time dilates and causality falters. Future telescopes vast in scale and space-based detectors of gravitational waves promise to probe deeper, seeking deviations that might unveil new dimensions or confirm the elegance of known laws. In this reflection, humanity stands at the precipice of the infinite, gazing into a void that holds the galaxy's fate. The emotional weight is palpable, a blend of awe, humility, and wonder, at our fleeting place within a cosmic order governed by unseen forces. Sagittarius A is not merely a black hole. It is the silent architect of our home, the unseen hand guiding the stars. Its presence challenges us to question the nature of existence, to seek truths hidden in the interplay of light and darkness. As the universe continues its eternal dance, this colossal enigma remains, whispering of origins, destinies, and the profound unity of all that is. The Milky Way stretches across the night sky like a river of frozen fire, its countless stars spilling into the blackness of infinity. For millennia, human eyes have traced this ribbon of light with awe and wonder, never suspecting that beneath its beauty lies a secret, a gravitational heart, invisible yet absolute, dictating the rhythm of our galaxy. That secret is Sagittarius A, the colossal black hole at the center of the Milky Way. 4 million times the mass of our Sun, yet compressed into a region smaller than the orbit of Mercury. It is a paradox incarnate, a place where matter vanishes, time slows, and space itself collapses under the weight of its own gravity. For centuries it remained hidden, until the dance of stars near the galactic core betrayed its presence, stars whipping around an unseen force with velocities so extreme that no ordinary object could account for them. And yet, even with all we know, the reality of Sagittarius A is far stranger than the simple label of black hole. It is not just a cosmic sinkhole where matter falls and light disappears. It is a gate into the unknown, an event horizon marking the threshold between what can be known and what may never be known. The silent master of the galaxy, without Sagittarius A, the Milky Way, as we know it, would not exist. It is the gravitational anchor holding together a galaxy of over 200 billion stars, countless planets, clouds of gas, dark matter, and cosmic dust. The spiral arms we see stretching like vast rivers of starlight are bound in their eternal rotation by its invisible grip. Every star, every world, every atom of life in this galaxy owes its stability in part to that dark center. Even our Sun, 26,000 light-years away, dances subtly to the rhythm of Sagittarius A's pull. And yet this master of the galaxy reigns in silence. Unlike some of its kin, active black holes blazing as quasars, consuming matter with furious hunger, Sagittarius A slumbers. Only occasionally does it stir, emitting faint flares of radiation, as though reminding us that it is still there, patient, timeless, unshakable. But beneath that stillness is raw power. Power beyond comprehension. Power to warp the very structure of space-time. Power to reduce suns into streams of plasma, torn apart atom by atom. Power to trap light itself, so that not even the fastest signal in the universe can announce what lies within, the edge of reality, what lies inside Sagittarius. It is a question no telescope can answer, no equation can fully describe. Einstein's general relativity tells us that within its event horizon, all paths lead inexorably inward toward a singularity, a point of infinite density where the known laws of physics break down. But infinities are not solutions. They are signs that our theories, brilliant as they are, remain incomplete. Quantum mechanics, with its rules of uncertainty and probabilities, suggests another story. That information might not vanish in a black hole. That matter might leave imprints, echoes, subtle traces woven into the fabric of Hawking radiation. Yet even this theory leaves us in paradox, trapped between frameworks that refuse to reconcile. Does Sagittarius A conceal a singularity, or something else? A bridge, a tunnel, a doorway? Could black holes be gateways to other regions of space-time, perhaps even to other universes? Or are they cosmic cul-de-sacs, dead ends where reality itself dissolves? No answer has yet prevailed. And in the shadows of this uncertainty lies the essence of the mystery, the mirror of human curiosity. The existence of Sagittarius A is more than an astronomical fact. It is a mirror reflecting back the questions that define humanity itself. Why are we here? What is the ultimate fate of matter, of energy, of time? Can the universe truly be understood? Or is there a horizon we cannot cross, a boundary where knowledge stops? Our ancestors once believed the heavens to be perfect spheres, immutable and eternal. Then came the revelations of Copernicus, Galileo, Newton and Einstein, each shattering old certainties, replacing them with deeper mysteries. The black hole is perhaps the most profound of them all, not only because it defies common sense, but because it forces us to confront the limits of science itself. To gaze at Sagittarius A is to confront the unknown in its purest form. It is to realize that there are places where our instruments cannot see, where our mathematics falters, where even imagination strains. And yet, rather than repel us, this abyss pulls us closer. The more unknowable it seems, the more urgently we long to know. The human horizon in 2019. Humanity glimpsed the unseeable, the first image of a black hole's shadow, captured by the Event Horizon Telescope in a galaxy far beyond our own. That achievement was not merely technological, it was symbolic. It proved that the impossible can be made visible. It suggested that perhaps one day, Sagittarius A itself could be revealed, its silhouette etched against the stars, its presence undeniable. Already, the EHT has turned its gaze toward the heart of the Milky Way, stitching together signals from observatories across the globe, straining to resolve that dark circle in the glow of infalling matter. Each data point, each pixel, brings us closer to confronting our galactic core face to face. And when we do, what will it mean? To see the very edge of space-time, to map the contours of an abyss, to hold in our vision the engine that has shaped our galaxy for billions of years. It will not end the mystery, it will deepen it, but it will also remind us of what makes us human, our refusal to stop asking, our unwillingness to look away. The cosmic paradox. There is a quiet irony in the black hole. It is both destroyer and preserver. It consumes, yet it stabilizes. It erases, yet it sculpts galaxies. Without it, we might not be here to wonder at all. And perhaps this is the ultimate truth Sagittarius A whispers, that creation and destruction are not opposites, but partners in the dance of existence. Stars are born, they burn, they die, and in their death they may feed the black hole. Yet around that same black hole, new stars ignite, new worlds form, new life takes root. The void at the center of our galaxy is not only an ending, it is also a beginning, the final question. So we return to the question that lingers at the edge of every thought. What does Sagittarius A truly mean? Is it a cosmic predator, destined one day to consume all that orbits too near? Is it a secret keeper, locking away truths about quantum gravity and the nature of space-time? Or is it something far more profound, a reminder that the universe itself is not obliged to be fully knowable? Perhaps the final answer does not lie in equations or in the shadows of event horizons, but in what these mysteries awaken within us. The awe, the fear, the wonder, the recognition that to exist in such a universe is itself a miracle, that to ask questions, even without answers, is to be alive. Sagittarius A is not just the center of our galaxy, it is the center of a deeper truth, that the universe is vast, dark, and endlessly mysterious, and that our hunger to understand it will never end. Closing reflection, look again at the night sky. Every star you see, every spark of light against the abyss, circles around a darkness you cannot see. And somewhere, far beneath that blanket of starlight, Sagittarius A waits, patient, immense, eternal. It does not demand to be known, it does not need our understanding. But still we search because that is what we are. Creatures of curiosity, explorers of the invisible, witnesses to the infinite. And so, the story of Sagittarius A is not just the story of a black hole. It is the story of us, of our endless attempt to reach beyond the horizon, to turn darkness into knowledge, and to find meaning in the silence of the stars. For in the end, perhaps the greatest discovery is not what lies within the black hole, but what awakens within us when we dare to face it.